All right, let's dive into a topic that trips up so many people, those really complex, tangled up electrical circuits. We're going to show you how to crack them wide open using a tool that's actually way simpler than you might think, Kirchhoff's voltage law. Have you ever just stared at a circuit diagram like this one? You know, the kind with a couple of batteries, loops going everywhere, and you just think, where do I even begin? It can feel like a totally unsolvable puzzle. If you've been there, you are definitely not alone. But I promise you, there is a clear, logical path through all that chaos. So, this is what I like to call the tangled circuit problem. It's that exact moment when the simple rules you've learned just don't seem to apply anymore, and you're left staring at a confusing mess. It's a classic hurdle for anyone studying physics or electronics, but today we're going to clear that hurdle for good. Look, you've probably been using Ohm's law, right? V equals I times R. And it's fantastic for those straightforward single-loop circuits. But the second you throw in another battery or more paths for the current to split, Ohm's law by itself just can't handle it. You need something more powerful in your toolkit. And that's where our hero of the day comes in, Kirchhoff's voltage law, or KVL, as we'll call it. This is the real key that's going to unlock all of those complex circuit puzzles for you. So what is this thing, really? Well, the official definition says that if you trace any closed loop in a circuit, any path that ends where it started, and you add up all the voltage changes along the way, the grand total has to be zero, every single time. It's really all about the conservation of energy. To make this super intuitive, just think of it as the hiking rule. Seriously. Imagine you're going for a hike. You go up some hills, that's like a gain in elevation. You walk down into some valleys, that's a drop. But if you complete the full loop and end up right back at your car where you started, what's your total change in elevation? It's zero, of course. A closed loop in a circuit works the exact same way with voltage. It's a beautifully simple idea. Okay, now this next part, this is absolutely crucial. This is where most mistakes happen, so let's really lock it in. It's all about getting your signs right. When we move across a battery from the negative side to the positive side, that's a voltage gain, so we give it a plus sign. But when we cross a resistor going in the same direction as the current, that's a voltage drop, so we give that a minus sign. Getting this convention down is the whole game. All right, so knowing the rule is one thing, but how do you actually apply it without getting all mixed up? Well, I've got you covered. I've broken it all down into a simple, repeatable, 4-step strategy that is going to get you the right answer every single time. Yep, that's it. Just 4 steps. This makes the whole process feel so much more manageable, way less intimidating. Let's walk through them. Step 1. Assign your currents. Just draw an arrow for the current in each separate branch. And here's the best part. You literally can't get this wrong. If you guess a direction and it's backwards, the math will just give you a negative number at the end, which tells you to flip the arrow. Easy. Step 2. Identify your loops. Pick your closed paths and draw a little arrow to show which way you're going to hike around them. Step 3. Write the loop equations. This is where we put KVL and our sine rules to work. And finally, step 4. Solve. You'll have a couple of equations, and the rest is just algebra. Okay, enough theory. Let's be real. The best way to get comfortable with this is to just do it. So let's put our 4-step strategy to the test right now. So we're going to apply our strategy to this little guy right here, a classic 2-loop circuit. We've got a couple batteries, 3 resistors. It looks a little messy, but trust me, our 4-step strategy is going to make this totally straightforward. First things first, we've already knocked out steps 1 and 2. As you can see, we've drawn in our best guesses for the currents, I1, I2, and I3, and we've defined our 2 loops, loop 1 and loop 2, showing the direction we're going to trace them. And now for the main event, step 3. Let's start by building the KVL equation for loop 1, following that path we just drew. Let's build this equation together, piece by piece. Starting our hike around loop 1, we cross that first battery from negative to positive. That's a gain, so we write down plus V1. Next, we go across resistor 1, and we're moving with the current I1. That's a drop, so it's minus I1 times R1. Finally, we cross resistor 2, again with the current I2, so that's another drop, minus I2 times R2. And the whole thing has to equal 0. Boom. First equation done. See? Not so bad, right? Now let's just do the exact same thing for loop 2. We just apply the exact same logic. This is where you really see how powerful and consistent this method is. Now pay close attention to the signs on this one. As we trace loop 2, we first cross battery 2, But this time, we're going from positive to negative. That's a drop. So we write minus V2. Now, look at resistor 2. Our loop path is going against the direction of current I2. So that actually counts as a voltage gain. We write plus I2 times R2. Then we cross resistor 3 with its current for a final drop. Set it all to 0. See how those sign rules just keep everything perfectly in order? And just like that, we're done. We've successfully translated the physics of this messy circuit into a clean system of equations. The physics part is officially over. All that's left is step 4. Grab these equations and use your algebra skills to solve for the currents. Okay, so let's wrap this all up. Let's pack everything we just learned into a handy little problem-solving toolkit that you can pull out anytime you're faced with one of these tangled circuits. Here are the absolute must-haves for your KVL toolkit. First, the core idea. The sum of all voltages in a closed loop is always 0. And to remember that, just think of the hiking rule. Second, be obsessed with your sign conventions. Positive for gains, negative for drops. Third, stick to that 4-step strategy every time. Assign, identify, write, solve. And lastly, my favorite little tip, do not panic if you solve for a current and the answer is negative. It doesn't mean you're wrong, it just means the real current flows the other way. The number is still correct. You know, when you think about it, what we just did was pretty cool. We took something that looked impossibly complex, and by applying a simple logical framework, we made it totally solvable. It kind of makes you wonder, doesn't it? If a clear set of rules can untangle a complex electrical circuit, what other chaotic-looking systems, whether it's in science or business or even our own lives, could we make sense of if we just found the right framework to apply? Something to think about. Thanks for tuning in.